We are at the network layer looking at the internet protocol. A few questions first. There's a lot of action at this layer, some rather straightforward, some very interesting. So we will cover all this functionality over the course of many videos. In this video, we will focus on some straightforward stuff, that of packet format and fragmentation and reassembly. So here is the IP packet format arranged in 32-bit blocks. So it begins with the version field, which specifies the version of the protocol. So we are in the process of transitioning from IP version 4 to IP version 6. We will cover IPv6 later, but henceforth we will focus on IP version 4. Why do you think this IP version appears at the very beginning of the header? Is there any reason for this, or it's just like that it has to appear someplace? Well, how you interpret the remaining fields is a function of which version of IP protocol you are following. So once you know the version, then you can interpret all these other fields. So it has to come at the very beginning. So following version is the HL field, which stands for header length. So this specifies the entire IP header in 32-bit words. So for example, if HL takes on a value of 5, that means the header length is 5 into 32, that is equal to 160 bits. But why do we need to specify this header length? This is arising because of this field options, which can be variable. Thereby you need to specify how long the header goes. Following header length is the type of service field. So what is the service that IP layer offers? Best effort service, no guarantees of any kind. But when people designed the IP protocol, they provided this field in case you want to treat packets differently. For example, if there is an audio packet, you can indicate that this is an audio packet by specifying some number as part of the type of service, which shows that this is an audio packet. And then that packet, because it needs some delay guarantees, you can potentially service it ahead of others. But this has mostly been of research focus, where the definition of type of service has varied over the years. Very few routers implement this aspect. It has not seen much widespread use. So following this is the total length field, which specifies the entire length of the datagram, including the header, in bytes. Note, this is not in 32-bit words, but in bytes. Then come the fields identification flags and fragment offset. This is to help in the fragmentation and reassembly that I mentioned earlier. But first, tell me, what is the maximum size an IP packet can take? So since the total length field is 16 bits, you can have 2 to the power of 16 minus 1 bytes, because this total length captures the byte count. So you saw in case of Ethernet that Ethernet can only take 1500 bytes as the payload in the frame, whereas the maximum size of the IP packet can be much larger than this. Typically, different physical networks will support different packet sizes. So if you have a big packet and your underlying physical network does not support it, you need to fragment that particular packet and reassemble this. We will cover more of this in the later portion of the video. Next comes the time to live field. We saw in the spanning tree protocol that when you build networks, some loops creep into the network topology, either because of fault tolerance purposes or misconfiguration. And whenever we have loops, you will see that the packets are going to go round and round. How do you help catch such packets? So are you thinking of token ring, the monitor catching the orphaned frames? Will that method work here? Who will act as a monitor in the internet core? There is no such monitor. So what should be done? If you went with the name, you could have thought, let me give an expiry date for each packet, let's say X seconds. So if the packet is still in the network past the expiry time, just drop the particular packet. Great, but what functionality will the routers need to implement this particular feature where they can detect that this particular packet is past its expiry date? So the routers need to be time synchronized, which is not easy to achieve in practice. So what this field typically has boiled down to is a hop count. So basically you start out with a default value here. Whenever the source generates this particular datagram, it sets the time to live equal to 64. The hope here is that the number of hops between the source to destination will always be less than 64 hops. So if it is taking more than 64 hops, that means it is doing rounds. So let's drop this particular packet. So the routers, whenever they receive this packet, they are going to decrement the field by 1 before forwarding. And if a router receives a particular datagram with this field equal to 0, that means that time has expired, or in this case the hop count is expired, just discard it. Next is the protocol field, which you must be familiar with from before. So this is the demultiplexing key that identifies the higher layer protocol. So if you want this payload, the data, to pass to TCP, you set this value equal to 6. If you want to pass it to UDP, you set it equal to 17. Then comes again another field which you are familiar with, which is the internet checksum. So this checksum is calculated only over the header. Why do you think that is? So when we talked about router design, we mentioned about the switching speeds, how a packet should spend the least amount of time in a router before getting out of the router. So if this checksum field is calculated only over the header, the router can quickly process the packet and get it out. The main characters in the packet format are the source and destination addresses. So these are 32 bits each. Without a destination address, there is no forwarding. So destination is the key to forwarding. So you also include the source address so that the destination can reply back to the source. So these addresses are unique, much like the addresses at the link layer, the MAC addresses that we have seen, and these are also independent of the physical network address. We will spend a considerable amount of time on addressing later. Following the addresses are the options field. These are rarely used in practice, but they are there in case you need them. So options can be used, for example, to record the timestamp. So as a packet goes through each router can timestamp saying I received this packet at this particular time. This can help in performance calculations, like how much time a packet spent at each router, what was the round trip time, so on and so forth. You could also record the route taken by a packet. I remember I mentioned that you can support source routing as part of datagram networks. So you can specify the source route as part of options, in which case the routers will use this route to forward the particular packet. Following this is the payload or the data. This is typically higher layer data, either TCP or UDP signal. So I mentioned fragmentation and reassembly before. So let's look at it in detail. Remember, our goal is to interconnect heterogeneous networks, and the problem is each of this technology has different maximum transmission unit. We call it MTU. So MTU stands for the largest IP datagram that can be carried within a link level frame. So for example, the Ethernet, the MTU is 1500. For FDDI, which is the token ring type of system, it is 4352. For PPP, which is the point-to-point link protocol, you have 296. In fact, this is a negotiable value between the sender and the receiver. For Wi-Fi, which is the wireless standard, this is 7981. When a source has some data to send, what MTU size should it operate at? What do you think? Do you think it has any idea of the path that is going to be taken by this particular datagram, and thereby know what the MTU sizes of the individual technologies along the path are? In which case, what should the source do? So it makes sense for a host to select an MTU of the link it is connected to. For example, if it is attached to an Ethernet, it should choose an MTU size of 1500. Now, if along the path at an intermediate router, if you want to forward this packet with an MTU size of 1500 over a technology with a smaller MTU, you will need to fragment this particular datagram. Fragment means divide up the particular datagram into smaller sized packets. Now, where do you reassemble this divided datagram? If you think next hop router, now the routers have to do the reassembly, which is going to add to the overhead. And as I said, routers, you want to make them really fast so that these packets can just zip past. And not only that, even if you did it, then there is again the danger that this datagram may again be fragmented at some point later in time. So the best place to reassemble the packet is the destination. So this figure captures this. So you have between host 1 and host 2, there are 3 different technologies. This is Ethernet, this is PPP, and this is again Ethernet. Now Ethernet payload size is 1500 bytes. This is 296. Remember, the Ethernet payload is 1500, but the IP header itself is 20 bytes. So this 1480 plus 20 add up to 1500. Now similarly, PPP I am using 296, again accounting for the fact that there is 20 bytes of IP header. It's going to be 276 bytes of the data that is going to be divided in this particular fashion. So 1480 gets divided in this particular fashion. And again, as you notice, I'm not reassembling the packet at R2. Whatever you obtain, you are just going to send it in this particular fashion all the way till H2, and H2 is then going to reassemble this particular packet. By the way, these values are not true in practice. Why? We will see shortly. Naturally, since you are doing this fragmentation and reassembly, you need to provide information for the destination to reassemble this particular packet. So this is handled via these 3 fields: identification, flags, and fragment offset. So the identification field helps identify a datagram. So all fragments are going to carry the same identification so that the destination will know that these are all fragments belonging to the same datagram and thereby put them together. There are 3 flags used, each corresponding to a bit. So the first bit 0 is reserved. This is typically set to 0. In other words, it's not used. When the second bit is set equal to 1, that means you are saying don't fragment this particular datagram. So if this bit were set equal to 1, and if it encounters a router, has to forward it over a technology that has an MTU size smaller than the datagram size, then it is just going to discard the packet, because it says don't fragment, but it has to fragment. Since it says don't fragment, it will just discard the packet. Now bit 2, which is the third bit, is more fragments bit, which is basically saying that there are more fragments to follow. So we will see this MF bit in action soon. So the last field is the fragmentation offset, which is 13 bits long. So this is going to measure the data payload in units of 8 byte blocks. So this offset basically captures where the data within this particular fragment starts relative to the original unfragmented IP datagram. So the first fragment will have an offset of 0. The later fragments will have different values. Again, an example will help understand all this. So here is our original datagram. This datagram is of length 1500 bytes, maybe because it's going over an Ethernet segment. I have specified an ID of X, and this flag is set equal to 0 and the offset is equal to 0. So this is the original datagram generated by the sender. So the data within this particular datagram is 1480 bytes because 20 bytes go towards the IP header. By the data within, I mean this is the payload, which is the TCP or UDP packet that is being contained. Now suppose I want to send it over a link with an MTU of 296 bytes. Now since the original datagram size, which is 1500 bytes, exceeds this NTU size, you will need to fragment this particular datagram. Now the question is, what is the maximum data, that is the TCP UDP data, that can be carried within this particular fragmented datagram? 276, right? Because we are dealing with headers, IP headers, and each of this fragmented datagram also needs to have an IP header. So you need to account for 20 bytes of header for each of this fragmented datagram. So 276 plus 20 add up to 296. But remember, I said this offset field is going to measure data in blocks of 8 bytes. Basically, what this means is whatever data you are carrying within a fragmented datagram has to be a multiple of 8 bytes. Given this, what is the data size that you can put in a fragmented datagram? So that turns out to be 272 bytes because 276 is not a multiple of 8. So you need to put only 272 bytes as part of the data belonging to a fragmented datagram. So here is the first fragment. So I have put the offset is equal to 0, which is indicating that this is the beginning of the particular datagram. Notice that I have set flag is equal to 1 because there are more fragments to follow. This has the same identifier as the original datagram, and the length of this is 292 because the data that you carry is 272, not 276, because as I said, it has to be a multiple of 8 plus 20 bytes of IP header. So for the second fragment, what do you think will the offset be? So the offset indicates the beginning byte of the particular fragment, but in multiples of 8. It is 34 because 34 is nothing but 272 divided by 8. And similarly, the third fragment starts at 68, which is 34 plus 34 and so on. So this is how it kind of goes. And as you can see, the flag is set equal to 1 because the more fragments are about to follow, and also the identification for all these fragments is equal to the X, which is same across all the fragments. Now the last fragment, which is the sixth fragment, what do you think the length field will be? And what will this offset be? The 5 fragments, the way we calculated them, should give you a good idea of how to determine what these values are for the 6th fragment. It's rather a simple calculation. So each of these 5 fragments are carrying 272 data into 5. This is equal to 1360. So the original data is 1480. So what amount of data that is remaining is 1480 minus 1360. This is equal to 120. The length field captures the header length also. So it is 120 plus 20, which is equal to 140. And this offset is nothing but 136 plus 34, which is equal to 170. And notice here that the flag is equal to 0, indicating that this is the last fragment of the particular datagram. No more fragments to follow. I guess you got the idea of how fragmentation is done. Now the receiver can look at these identifier fields to put together all the fragments belonging to a particular datagram, and it will use the offset field to put them in order. So that's it with respect to this video. We looked at the IP packet format. It has a variety of fields. An important aspect here is the fragmentation and reassembly, which is arising because of our need to interconnect heterogeneous networks. We saw how the offset field and the identifier help reassemble these particular packets at the destination. Up ahead is the addressing that is employed by the IP protocol, as well as how to forward packets based on this particular addressing.